Hello and welcome. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today we're going to be going over another very common machine learning model, and that is the logistic regression model. We're actually going to be building it from scratch. So I have done a video prior to this one on what logistic regression is, very high level. Recommend you go check that out before this video. It's not a very long video, so it shouldn't take you very long to get through it. But you kind of want to know those high level how it works before you jump into this. We're actually going to be implementing some of the math and code here, so it's a little more fun in this video, a little more interactive than sitting down with some slides. But without further ado, let's go ahead and jump over to the Jupyter Notebook. Okay, over in the notebook, you can see we are ready to go ahead and get started. So first thing we need to do, like always, import some packages. I'm going to be using Numpy as the backbone for most of the code in here, so let's go ahead and import that. Next, I'm going to be using matplotlib pyplot in order to visualize some of the data. And last, I'm going to be importing some sklearn packages. Now, I'm not going to be importing the model because we're going to be making that, but we're going to be importing some tools to help us create the data and pre-process the data a little. So, from sklearn, we're going to be importing data sets. Next, from sklearn.model selection, we're going to be importing train test split. And the last thing we're going to do is from sklearn.metrics, we are going to be importing accuracy score just to help us figure out how well our classifier is working. All right, go ahead and run that. If you haven't heard of any of these modules, I do have tutorials on each one of these. You can go ahead and check those out, but not going to be super important for you to know the as long as you have a basic understanding or can follow along, it's not too big of a deal. All right, first thing we need to do, as with any machine learning problem, is we need data. So we are going to define a function called genData. And this is going to be using that datasets module that we just imported. So data is going to be equal to datasets dot. We're going to be using make moons. Now, I've used this before. If you haven't seen my previous videos, don't worry. I'll show you exactly what this make moons function does. It's pretty intuitive once you see it. But what it's looking for is number of samples. And let's go ahead and make, let's just do 1,000 samples. Next, it's going to be looking for some noise. So how pristine do we want our data looking or not? So I'm going to import, let's see, noise equal to, let's go 20% noise. So 0.2. And last thing that I'm going to do is I'm going to fix the randomness so that you can repeat exactly what I'm doing here and get the same results. So random state is going to be equal to 1. That is going to make our data set. Now, if you want to make this a little more robust, go ahead, throw all of those variables up in the actual function so that you can change them on the fly. I already know what I want, so let's go ahead and leave that. Now, I want to also see the data just so you can see what it looks like and so I can see what it looks like. So plt.scatter, get my mouse out of the way. I'm going to be taking the data at 0, taking the x values. I'm going to do a transpose, so .t, and I'm going to take the first feature. Now, I'm going to do the same thing, so I'm just actually going to copy this over, but I want it to be on the second feature, so index equals 1. The last thing I'm going to do is I'm going to change the color to be equal to the data at 1, so the output color. And I will do a plt.show. Oh, sorry, let me close my function here. Push this plt.show over. Last thing, I need to return the data back to the main cell. Okay, we can go ahead and use this function. So I'm going to say x and y are going to be equal to genData. Last thing I'm going to do is I'm going to split it into training and test sets right away. So x train, x test, y train, y test is going to be equal to train test split. We're going to be passing in the x values, the y values. It's looking for the test size, which means how many data points are we saving for the test data set, we are going to use 20% of the data. And again, I'm going to fix the random state to 1 just so you can repeat exactly what I'm doing here. Go ahead and run it, and you can see the make moons function makes moons. So these little arcs right here, and it's a binary classification. We only have 2 classes here. So this is what we're going to use for our data. Now that we have the data, we can go ahead and start working on making our logistic regression model. To make it, we are going to be using a Python class. So class, I'm going to call this Logistic Regression. And the first thing we need to do is initialize it. So define init. The only thing that I'm going to pass into it is I'm going to pass a value called rand, and I'm going to assign that to -1. I will show you what I'm going to do with this, but it's again back to I want to fix my random states for you guys, and this is a way that I can pass in different values for that random state. Okay, now we can start initializing some variables. There's only going to be a couple, so self.weights. So these are actual weights in the network. I'm going to just start with none because I want to know if they've been initialized or not, and the none will tell me that they haven't been yet. And the other thing is just going to be saving that random value as self.rand. Okay, that's our initialization function. I do need another function to initialize the weights, so I'm going to call this init weights. And this is going to take the x data. So first thing I want to do is use that rand value that I just made. So if self.rand does not equal -1, then I'm going to fix the randomness. If it does equal -1, we're just going to allow randomness to occur within the model. So to fix the randomness, I'm going to do an np.random.seed, and I'm going to pass in self.rand. Whatever value I pass in for rand when I initialize it is going to be put in here for the seed. And if I don't want to, again, it's going to pass -1. It's just going to pass right through that, and our values are going to be random. So to initialize the weights, I'm going to do self.weights is going to be equal to np.random.rand, and this is going to be x.shape of 1. So I'm going to take axis equals 1, the shape of that, and make that many weights. I'm using random values for the weights. You can do this as 0 values if you want, or whatever value you want to put into it, but I'm just going to do random values for the weights. Okay, let's go ahead and start defining our fit function. So define fit, and fit is going to take x values and y values for now. Okay. As I mentioned before, we are initializing weights to none. So if the weights are still none, we do need to go ahead and run this initialization function. I'm going to start that off right in this fit function. So if not self.weights, so if this value is still none, it's going to pass into this if statement right here, and we're going to run the function. So self.init weights. And again, that's looking for x. Okay, now that we have that, we can go ahead and start training our model. So in training, we are going to be running our data through it for however many iterations that we want. Now we do need to pass that in. So I'm actually going to make that another input value for the fit function for epochs. And I'm going to set the default to 10,000. So how many times we're going to run through our data. And I can go ahead and make the for loop by saying for epoch in range epochs. And this is where we start looking at predicting and then running the gradient back through it. So first thing, to get our values, we're going to say z is going to be equal to np dot. So this is the dot product of the x value, the input feature values. We're going to take that and we're going to do the dot product with self.weights. Multiply through all the weights. And then, again, if you saw my video before, we have all these, but we need to pass it through an activation function. And we are going to be using sigmoid as our activation function, which we do need to define. So up above fit, I'm going to go ahead and define that. So define sigmoid. And sigmoid is going to just take that z value. So I'm just going to call it z. And it's going to return. I'm just going to do floating point because it's going to end up that way anyway. So 1.0 over 1.0 plus np.exp. This is e to the power of whatever I pass into it, which will be negative z. Okay, that's all sigmoid is. So we can go ahead and jump back down to the fit function and go ahead and use it. So y hat, or the predicted values for y, is going to be equal to self.sigmoid. We're going to pass in z. Okay, now we've made it through the first half. We got our predicted values. Now we need to come up with the gradient in order to update our weights. To come up with the gradient, I'm actually, again, going to define another function right above the fit. Call it gradient. Gradient is going to take the x values, the real y values, and the predicted y values. So x, y, and y hat. It is going to return the dot product, np.dot, of the x values. And then I do actually need to transpose the x values first. So the transpose x values, we're going to be doing the dot product between those and the difference between the real y values and the predicted y values. So y minus y hat. And that is going to be our gradient. Jumping back down to the fit function, we can go ahead and update the weights. So self.weights is going to be equal to self.weights plus, they're going to be adding the learning rate. And we haven't defined learning rate yet, so let's go up to the fit function, have that as another input, learning rate. I'm going to set the default to 0.001. I'm going to take that learning rate and I'm going to multiply it by the gradient, which is the function that we just made. So self.gradient, I'm going to pass in x, y, and y hat. And that is going to take care of adjusting our weights. So that is pretty much it for our fit function. I do want some other functions to track the progress. So I want to know the loss over time. And since this is a classification problem, I'm going to define a new function called log loss. And log loss is going to take the real values of y and the predicted values of y. Now, some of these values may be equal to 0 or 1. I actually want to kind of correct for that just by making an epsilon value, which is going to be equal to a super small number. So 1e to the negative 15. And then I'm going to take the predicted values of y hat. And I'm just going to do a y hat dot clip. And I want to clip to epsilon and 1 minus epsilon. So this is going to take care of the zeros and ones and put them to epsilon for the lowest and 1 minus epsilon for the highest. Just because we're about to use logs and it'll mess it up if we don't. Then I'm going to return negative np.mean. Okay, so log loss is y times, let me just space this out a little bit, np.log of y hat. And then we're going to add 1 minus y times np.log of 1 minus y hat. And that is the log loss equation. Okay, that takes care of that. Jumping back down to the fit. Every time we run through this, I want to save that. So I'm going to say loss is going to be equal to log loss. I need to pass it in the y values and the y hat values. That is going to give us the loss value. I'm going to jump up above the for loop now, and I'm going to make a losses variable as a list, just a blank list. And then every time we run through this, I want to just append that loss. So losses.append loss. This is going to keep track of the loss over time. One more thing I want to do is I do want some status messages every few epochs so that I know that it's going in the right direction. To do that, I'm going to say if the epoch, so whatever the current epoch is, plus 1, because we're starting at 0, if the current epoch plus 1 mod, I'm going to take the epochs and divide by 10. What is this doing? Well, it's taking, this is going to give me 10 status messages over the entire training period. That's why I'm dividing by 10. If you want a different number, divide by a different number. And then it's going to take care of whatever that is equal to. Say if I change my epochs, I don't need to change this output message. But I want to know whenever this is equal to 0. Or I also want to know when the epoch is equal to the epochs minus 1. So when I'm on the very last one, because I want the status message for the very last one as well. Okay. Now, if either of these are true, I want to print a status message. So I'm going to be printing the epoch first. And the epoch is going to be equal to the string of the epoch plus 1. I'm going to add in a division sign. And then I'm going to add in another string for the total number of epochs. This is just going to give the current epoch over the total number of epochs. And then the last thing I want to do is I want to record what the loss was. So I'll pass that in with a little divider there. And I will print out the loss. Okay, this gives me my status message. Now the very last thing that I'm going to do before we finalize this fit function is I want to just graph the loss so I can see the loss over time. So that's going to be a plt.plot for the range of length of losses. And then I'm going to be plotting the losses. And then plt.show. Okay, this takes care of the fit function. We can now train our model. That's great. Now we need to be able to predict, though, because we may be able to train it, but we're not going to know how well it's doing. So I'm going to define two prediction functions. First, this function is normally going to print out a value from 0 to 1, just a floating point. So I'm going to call this predict proba, and this is common in sklearn. This is also how they define it, so I will keep it the same. And we're going to be passing in x. And now, if you remember way up here to the top of the for loop in the fit function, this y hat is taking the dot product of the x values and the weights and then passing it through the activation function. So this is exactly what we need right here. I'm going to copy all of this down to predict proba. That will give us our y hat values, and all we need to do is just return those y hat values. Okay, great. Those will give us values 0 to 1 based on the probability of it being in that class. I don't necessarily care for scoring of what the probability is. I do want to know if it's over a certain threshold to say that it's either a 0 or a 1. So I'm going to define another function called predict. And again, it's going to be self, and it's going to take x. I do need to get those probabilities to start with. So I'm going to say y hat is equal to the function that we just created. So self.predict proba, passing in x. Okay, this gives us all of the values 0 to 1. Now we need to account for whether they are below or above 0.5. So y hat is going to be equal to wherever y hat. Oops, that's not equal to. Passing in here. So y hat where y hat is greater than 0.5. I want that to be equal to 1. Anywhere it's greater than 0.5 is equal to 1. I want to do the opposite for less than equal to 0.5. So copying that down, changing this to less than equal to, and saying that is 0. So this is just going to give us zeros or ones depending on what the probability is. And we can go ahead and return y hat. And that will conclude our logistic regression model. And we can go ahead and now test it out by training some data and predicting with it. So CLF is going to be equal to Logistic Regression, the class that we just made, and I'm going to pass in rand equals 1 because I want to fix the random state. I'm going to do a clf.fit. I'm going to pass in the training data, so xtrain and ytrain. And that will go ahead and fit the data. So let's see if I have any errors, and I do, and that is down here in the status message. There should be a double equals. I have another one as well. Log loss is not defined because I need this to be self.logloss. And there we go. As you can see, working through 10,000, the loss went down fairly drastically, and then it sort of leveled off. So exactly what it should be doing, but we need to make sure that it's actually predicting correctly or accurately based on whatever you want it to be. So preds is going to be equal to clf dot, just going to do the predict, and we're going to be passing in x test. So passing in the x test values, giving us predicted values for y, and now we want to print out the accuracy, which is going to be equal to accuracy score. This is one of the functions we imported from sklearn. We're going to pass it in preds and the y test values. So predicted values and the real values. Go ahead and run that. I didn't close my parenthesis. There you go. We got 89% accuracy on our data that looks like this, which is fairly good. There are ways to improve this. We can make this a neural network, add in some hidden layers, but for now, that's where I'm going to stop. That is logistic regression. Again, fairly easy to implement. And if you haven't seen the video already, I do the same thing as I'm doing here, but for linear regression. And again, like this, it's fairly easy to put together and follow along. So definitely go check that out. If you got anything out of this, please like the video and subscribe to the channel for more stuff like this. I will be using logistic regression to solve some real world problems, so stay tuned for those. But for now, I am out, and thanks for joining my video.